Hello students, now we are going to take the last review of the chapter called Work, Energy and Power. Chapter 9, Work, Energy, Power. This is a small chapter, doesn't have much of lengthy things, but it is also a very important chapter which has quite a bit of derivations which will be very important for you. So this has three topics: work, energy and power. So work means you have all the things related to work alone, it will be there. So work done, the definition, what is work done, and then you have the basic vector quantity f dot s is equal to fs cos theta and is equal to dot product f vector dot s vector. These things are there, and then you have the three work done, which is called positive work done, negative work done and zero work done is there, and the fourth part is variable work done. So if I look at this one, it is mainly work is only work done, and conservative force is there. The conservative force, you will be seeing this one. So children, when you are doing this, I would say don't waste time on the first few pages. These are all things you should know before itself. So just take a quick look. Various different type of forces are there and examples are there. Zero work done, everything you know it very well. 9th standard you have studied. And also variable work done, that means work done is going to be equal to area of the graph. So these things, please don't spend much time. These are all only numerically, it will come more. And also you've got to see about the conservative and non-conservative force. What is conservative means? If the work done by the force, it depends on the initial and the final position alone, then it is called conservative force. First starting here and then ending here, that's all. So starting down and starting up, it is just all. It just starts with the A to B, that's all. That means it is only it's a conservative force. If it is involved in every path it is traveling, then it is called non-conservative force. So the work has work done and conservative force. The conservative force, there are three derivations are there, three examples, and it's a very simple derivation about mgh. Please do that. The next one is energy. Energy is the ability to do work. So we have two varieties. It's called kinetic energy and potential energy. This entirely comes under the mechanical energy. So E is going to be equal to U plus K. That is a usual thing that will be there. This is total energy and this is potential energy. U means potential energy and K means kinetic energy. So this is the typical combination. E is equal to U plus K. You should understand that is mechanical energy, total energy is going to be equal to kinetic energy plus potential energy. It is a kind of an together it goes. So when you do kinetic energy, you will do a derivation called work energy theorem. The change in kinetic energy, delta K is going to be equal to work energy theorem means, so the kinetic energy of half mv square minus half mu square. So final kinetic energy minus initial kinetic energy, that is going to be equal to delta W. Delta W will be there, the change in work done. The work done is going to be equal to this much. That is called work energy theorem. So if you look at kinetic energy here, kinetic energy is right here, and then the next page derivation is very important, work energy theorem. It comes here, alright, and it has a full derivation here. Please, it is a integration. So work done is going to be equal to, change in kinetic energy. Okay, half mv square minus half mu square, that is W. So that is the one that you have. Please learn this one derivation properly. And there is a small part, kinetic energy and momentum, how it is there. There is a graph is also there. So this part is also important. Okay. Now once you have done this particular part, work energy theorem, then the potential energy, it comes. It is potential energy due to gravity, acceleration due to gravity. So what do we call as mgh? And then potential energy due to the spring, that is half k x square. Two potential energy we will be deriving. So if you look at this potential energy of a ideal, that is the first part is the gravitational potential energy is here, mgh is there, okay, and then potential energy of the spring is detailedly it is explained. So the first part, it is a force, restoring force is going to be what it is, derivation starts here, and then you go on to derive this one, W is going to be equal to half kx square. Whenever you put U, that is called potential energy. U means potential energy, right? Half kx square, you have derived this one. There are two graphs on this. One is the force, restoring force and displacement, then it is a straight line graph. So that is called this one. And the next graph is the graph like this. Okay, this is also a graph which says about the kinetic energy and potential energy, how it changes. So that is there. The next one is principle of conservation of energy. It is dealt with the energy also is there. In energy, conservation of energy is there. So you have to say one example. The one example is the gravity, when it goes under gravity. So there are 3 points are there, A, B and C. You know this derivation how it is. So A part, what is the total energy, B part, what is the total energy, C part, what is the total energy. This whole derivation comes with the graph. So you get here the bigger picture of this one, work done and conservative force. Work energy theorem, work done due to gravity, that's what we saw about the conservation of energy also it is there. And then work energy, this one is due to the spring. Derivation 1, derivation 2, derivation 3 and conservative force 1 derivation is there. And these are all definitions are there, that's all. 1, 2, 3, 4. Okay. The next one is power is a very, very small part with just a definition is there. There's nothing much in it, right? Then you straight away get into the last topic of collisions. Collisions is the final topic which has a very long derivation. It is a very big derivation it's there. So two bodies are coming and colliding each other, how it comes, and then you call about coefficient of restitution, the velocity of reapproach is equal to velocity of approach, the relative velocity and all these things, and finally this formula is derived. So this formula, when you derive it, please remember you should be able to write this formula without seeing anywhere, right? So V1 is going to be equal to upon M1 plus M2, please write this one, and M1 plus M2. So both the masses are always added, and then here M1 minus M2 will come into U1, and here 2 times of M2 U2 will be there. That is the V1. You should definitely know how to write this one. Any time if you should be able to write this one. You mess up anywhere, you bring out in the final formula and park it, that's also okay, because you have anyhow known the last formula. What is our V2? Same thing, M1 plus M2 will be there, and then plus M1 plus M2. Only what you need to do is, wherever 2 is there you put 1 in the numerator, wherever 1 is there you put 2. So 2 M1 U1, and here M2 minus M1 into U2. This is done. So you will get quite a bit quick things, and it has a lot of special cases over there. Please remember all the special cases are important. We have done 7 cases in the notebook clearly. Please learn everything. So with that, this chapter theory portion comes to an end. So there was a 2-dimensional collision. I told don't do it. You need not do that. And also inelastic collision. There are 2 collisions are there, elastic collision, inelastic collision. So inelastic collision, you don't do that. So the bigger picture is, this formula comes only under a very important called elastic collision. Now you can ask me, sir, what is elastic collision? Elastic collision means the initial kinetic energy is going to be equal to final kinetic energy. There is no loss in kinetic energy. That's what the elastic collision means. In elastic collision means there is a loss of work. Delta W is going to be equal to final kinetic energy half mv square minus half mu square. When you have a loss, you need to, this will be greater, this will be less, and there is a loss in work done finally. That is called inelastic collision. Okay, elastic collision, inelastic collision. Inelastic collision means you have an energy which is lost, kinetic energy which is lost. Here, both the initial kinetic energy and the final kinetic energy, nothing is lost. Okay, so that is what the beauty of this one is. Hope you got it. So this formula comes under elastic collision. Please remember, this doesn't come under inelastic collision. This formula doesn't talk about loss in kinetic energy. This formula talks about only the equal kinetic energy. Initial kinetic energy and final kinetic energy equal. So please remember that. So followed by numerical examples are there. There are so many examples. We already did it. Please remember to learn everything. You had a separate test only for numericals, even though many of you didn't do so well. But this has such a lot of numericals. Look at this one. It goes on and on. I already told when we were doing it, went on to 961 numericals are there, and some numericals I already cut down. You know it. You please learn that one. And plus you had numerical problems. Here also there was 40 numericals. So this has quite a lot of numericals, right? So derivation wise it is not so much, but numerical wise it is pretty strong. And remember, this particular chapter has quite a lot of things common with the laws of motion also. Laws of motion, whatever you did about conservation of momentum, it will come here also. In laws of motion, if you talked about force, that force also a bit comes around here also. So in general, this chapter to do it, if you want to do it because you already done recently, the theory portion, if you just quickly revise, the entire chapter will get only 1 hour, and then for the numericals, you need to go through that whole thing. It will take another 2 hours. Within 3 hours, I would say this whole chapter should have been finished. So work, energy, power, work separately, energy separately, power separately, and the main topic is collision. Collision is the final thing which comes. So I already told about work and conservative force. Energy has work energy theorem and potential energy of gravity and potential energy due to spring. This one is a very important derivation. And then power, and then last part is collision. Okay. Okay children, wish you all the best. Do well. Practice well. Thank you.